All right, let's look at some u-substitution integration with inverse trig. And working these problems, we are working under the assumption that you know your inverse trig derivatives. If not, you have 2 seconds to write those down and have those off to the side so you can study them. 1, 2. Okay, moving on. And this is a set of those same formulas, only uglified and going from right to left. What I've done here is I've included ugly functions, which is tying in the chain rule, which is where u sub comes into play. And for all of these where I have u prime and u squared and all that mess, u is some function of x. And so these are some formulas that will expedite the process of solving antiderivatives involving inverse trig. There are longer algebraic approaches you can use to solve these, but we are looking for efficiency, so I do recommend that you remember these formulas because it makes things significantly faster. So let's do a few examples, and they're going to gradually increase in difficulty, starting with this one. You could, and what I'm about to do is actually incorrect, so don't copy this down just yet, but you could start this one by thinking u is equal to the entire denominator, which is a very common approach to u sub. The problem is when you do the derivative of sine squared, it ends up being 2 sine x to the first and then times the derivative of sine. And with u sub, the most important part is you must identify u prime in the problem, and I do have the cosine and the dx. I am missing the sine. That is a huge issue, which means this u sub fails. And so on this problem, and this is fairly common, especially when you have trig functions, I'm actually going to identify the u prime, my du, before I identify my u. And so this would be a great choice for u prime, the cosine x dx, if I could somehow let u equal sine x. So if u is sine x, there's my u prime. So that's what we're going to attempt. So u is sine of x, u prime, the derivative of sine is cosine x dx, and there is the u prime. So when you do the substitution, this would turn into cosine x dx is my du, so I stick that off to the side. My numerator was wrapped up in the du, so I'll put a 1 up there to hold its place, and on bottom it's 1 plus sine squared, and sine is u. And 1 over 1 plus u squared, you should recognize that as the derivative of arctangent. So that's arctan of u plus c, but we started with x's, we must finish with x's, so my final answer is the inverse tangent, or the arctan of sine x. For now, we will stop there. There actually is some algebra that you can sometimes do to clean up the composition of trig functions like arctan of sine and stuff like that, but in this case we won't be doing that. Actually, this one I'm not sure cleans up much anyway. But moving on. So there's number 1. Number 2, same type thing. You could try letting u be the bottom, but if you let u be the denominator, your u prime is 4x cubed, and I don't have an x cubed, I have an x to the first. Accounting for missing variables is kind of tricky, so I avoid it when possible, and this is avoidable. And again on this one, I'm almost going to let the u prime pick the u. I'm looking at 2x dx, and you should recognize 2x as the derivative, that would be u prime, if I could somehow let u equal x squared. So I'm going to attempt to see what happens if I let u equal x squared. If I do, u prime is 2x dx, which is great because that's already in the problem. As far as identifying the x squared and taking care of the denominator, if you wanted, you could rewrite this problem as 2x over 1 plus, and x to the fourth is x squared squared. And if we do that, now we have our u prime right there. So there's a du, and then my u is right here. And so what we end up with is the exact same antiderivative we had a minute ago, 1 over 1 plus u squared du, which is the derivative of arctangent x, or arctangent u. So we have arctan of u, but u is x squared plus a c, and there is your answer. So you're trying to steer it in the direction of those memorized inverse trig derivatives, which you all should have memorized by now. Lazy bums. Y'all haven't memorized them, have you? All right, so moving on. So we have e to the x over root 1 minus 2x, and this one has a radical in it, which often the presence of a square root can trigger your thought on inverse trig, because if you look at the derivatives of, say, arc sine x, inverse sine, or inverse secant, both of those do involve radicals. So if you see a square root of like 1 minus something, or something minus 1, that often can be steered in the direction of an inverse trig antiderivative, and this one's no exception. In this case, I notice my numerator is e to the x dx, and I really want my numerator to be my u prime. I really want that to be my u prime. And so I think that e to the x, that's a good u prime if I could let u be e to the x, because e to the x is the derivative of e to the x, and so let's attempt that. U is e to the x, u prime is e to the x dx. And again, kind of like the last problem, we can make this work. It might help to rewrite it. So maybe I'm going to rewrite this as e to the x over the square root of 1 minus, and e to the 2x is the exact same thing as e to the x squared. So now when you look at the substitution, there's my u prime, there's my du, same thing as u prime du. What's wrong with my u? Du, whatever. Alright, then on bottom, I have the square root of 1 minus e to the x squared, and e to the x, right there, is my u. So when I rewrite this, when I do the actual substitution, e to the x dx is my du. My numerator is gone, so I'll put a 1 to hold its place, and in the bottom, I have the root of 1 minus u squared, and that you should recognize as the derivative of the arc sine of u. But u is e to the x, so we'll go back and we will plug e to the x back in for the u. So arc sine of e to the x plus c. There we go. Let's see, what do we have next? Okay, so this one, we have 1 plus 9x squared, and a while ago I put up a page with some memorized formulas that were a little bit ugly, and this is where these are going to come into play. Where I had like u prime over a squared plus u squared, this a is accounting for the fact that it's not 1 plus x squared. This would be really easy if it were 1 plus x squared. It would just be the normal arctangent of x. But the fact that that's a 9 is changing it, so what I'm doing here, if a squared represents 9, then that means that in this problem, my a value is 3. My u prime, if I let u equal x, u prime is 1. And so I have my u prime over 9 plus u squared, and this one is about as clean a problem as you can come up with that involves those a's. This one is almost arctangent, so it will be the arctangent of u, but my a is 3, so it's going to be 1 over 3. The answer is actually going to end up being 1 over 3 arctangent of u, which is x, over a, which will be 3, plus a c. There are some algebraic options and some factoring and some other things you can do to prove that that's what it ends up with. However, for efficiency, it's probably better for you just to know that formula, that when you have like a number plus x squared or a number minus x squared that isn't a 1 plus or 1 minus, then you've got to think about these formulas right here, and these account for non-1 values of a. So moving on, that was 4, here's 5. Same thing, I see a square root of something minus something, and now they're both ugly. So what I'm going to do here is I'm going to rewrite it as x over, and 25 is 5 squared, minus, and 9x to the 4th is the same thing as the quantity 3x squared squared. So I'm rewriting the problem so that I see something squared minus something squared, because the formula I gave you a minute ago was this one right down here, where I really want to see something squared minus something squared. So in this problem, what I'm seeing is my a value is 5, my u value is 3x squared, because that's what's being squared, but then on top, that needs to be u prime. So if u is 3x squared, u prime is going to be 6x dx, and I have the x, but I'm missing a 6, and that's okay. We can accommodate for missing constants. So I'm going to stick a 6 here. I'm going to offset it with a 1 over a 6. And now what I've got is I have u prime over the square root of a squared minus u squared, which is exactly this formula, which ends up being the arc sine of your u, which is 3x squared, over a, and a was 5, plus c. And that is the antiderivative. Don't forget that if you ever have to insert values to keep that 1 over 6, in this case it's 1 over 6, in the answer. And so there we go. So it's all about identifying that a and that u and making sure the u prime is accounted for. And that's how we're going to use these formulas, the u prime over root stuff, to get the antiderivatives of inverse trigs. Let's try this one. So we're looking at number 6 here. And this one might introduce a new situation for my students. I am looking at this one, and it looks an awful lot like my formula for the antiderivative of arcsecant, which is right here. So when I'm looking at this, the only easy thing to see in this one is that I have minus 1, which means my a value is 1. So my a is 1, which is going to make it a little bit nice, but also remember that you want it to be something squared minus 1, and u to the 4th is the same thing as x squared squared. And if you need to rewrite it, 1 over x square root x squared squared minus 1. It might help, I'm not sure. It's a very subtle difference. My a value is still 1, but now I can see that the thing being squared is x squared. Well, if that's my u, I've got to find u prime. If that's my u, I've got to find a u prime, and the derivative of x squared is 2x dx. And here we are about to see a new situation and a new way to account for your u prime. I've told you that in every u sub problem you absolutely must account for u prime. There's no exception to that. Every time you do u sub, you must see u prime in the problem. The issue here is I don't have any x's up here. So far, every u sub we've done, we've been able to account for missing constants. And if I want to account for that missing 2, I could easily multiply the top by 2. I don't want to multiply by dotted 2. Let's try. Multiply the top by 2. And if I multiply the top by 2, I multiply the outside by 1/2, and that takes care of the 2, no different than how we accounted for the missing 6 in number 5. However, if you are missing variables, it is possible to account for missing variables. I can put an x in here to account for the missing x. The thing is, if you put a variable in there, you are not allowed to come to the outside and plug in a 1 over x over there. If you plug in a missing variable, you account for that by putting it inside the antiderivative. So if I put an x on top, I'm going to put an x on bottom, but I'm going to keep it in the integral, not outside. Then if you look at what that created, I now have 1/2 antiderivative. I have 2x over stuff with a dx over here. Notice that when I put that x down there, it became x times x, which is x squared. And then I'll keep this as x squared squared minus 1. And if you look at that, my u prime is right there. And for arcsecant, you're supposed to have u squared minus a squared, and that's exactly what we have. I have u right here, because u was x squared. I have another u right here, because u is x squared. And then my a is still 1. So this antiderivative turned into this exact same formula, which is 1 over a arcsecant of u over a. So my answer is going to be 1 over a, which is 1, arcsecant of u, which is x squared, over a, and a is 1, plus c. And then don't forget, and this almost snuck away from me, I did put a 1/2 out front, so that 1/2 needs to come along for the ride. And the answer really ends up just being 1/2 arcsecant of x squared plus c. There we go for number 6. That's probably going to be the hardest one. I can't remember what 7 looks like. But missing variables, just know that if you need to insert a missing variable, you can, but you have to account for it within the antiderivative. You cannot stick it on the outside like you can with numbers. So let's see what happens with number 7. And 7 looks really bad, but it actually is going to end up being fairly clean because it's 1 over something plus something squared, which looks an awful lot like this. Um, and in this problem, what I see being squared, the function being squared is x minus 2. So I see a u of x minus 2. The number squared, I have a 16, so my a value is 4. And then u prime is 1 dx, and I already have my u prime on top. So this problem is already in the form u prime over a squared plus u squared, which ends up being 1 over a arc 10 u over a. So the answer is going to be 1 over my a, which is 4, arc 10, of u over a, which would be the quantity x minus 2, over 4, plus c, and there is your antiderivative. So there is a crash course on some antiderivatives involving inverse trig. You must learn at the very least, you must learn these basic trig derivative formulas. It is a huge help if you can remember these formulas right there.